Guys, hey guys, this is a video on vector spaces. So our topic, this is a learning video on vector spaces. Okay, so I'm Thakur. Okay, so what is a vector space? The question comes about what is a vector space. So what is a vector space? Well, that's a question. What is a vector space? A vector space is composed of vectors. So it's composed of vectors. So you'll say, okay, what type of vectors? So there are many vectors. So what vectors do you actually choose for making a vector space? So the answer is you choose vectors. Now, so what are vectors? So the question is, what kind of vectors? What kind of vectors we're talking about? So, well, we're talking about vectors, vector spaces, and they are composed of rules. So we have rules. We can't do anything we like in the vector space. We have rules. We have, in general, two rules, 1 and 2. First is addition of vectors. The second is multiplication by a scalar. No, I'm just to emphasize, I'm talking about multiplication by scalar quantities. I'm not talking about multiplication of vectors with a vector. So multiplication by scalars. So if we have a vector, say this is a vector x1, x2, and x3. Say this is a vector in the R3 space. Then we can add it to a vector. Y1, y2, y3, and the result would be some x1, y1, x2 plus y2, x3 plus y3, again lying in the R3 space. So a vector space is that you do addition of vectors, you do multiplication by a scalar, and the result will lie in the vector space, in the vector space itself. So everything has to be in the vector space. You can't go out of the vector space. So you see, well, okay. So vector spaces. Nice. So what about now the properties? Addition of vector spaces, multiplication of vector spaces. Addition, as we know, is that if we have a vector capital X denoted by capital X, and that is denoted by capital Y. So if capital X belongs to the R3 space, for example, and capital Y belongs to the R3 space, and then we can associate to them a vector x plus y also lying in the R3 space, so that we call it the addition of vectors. So that is about addition of vectors, and multiplication by scalars. And now together, how do we say these both things at once? These both things at once can be said that we can take linear combinations. So we can take linear combinations, LC for short, and we will lie in the same space. We take linear combinations, we lie in the same space. Okay, so that was about a vector space. And what is a vector space? So that is a vector space, and we have, of course, many properties for addition of vectors. It's commutative, it's associative. Those are the basic laws of algebra. So algebra vectors. So we don't discuss them because they're very, very elementary in nature. So okay, that's fine. Now, what about subspaces. There are some things known as subspaces. So let's approach what is a subspace. A subspace is like it's a vector space is like a big picture, and subspace serves like a small picture. A subspace. A subspace is what is a subspace? Okay, so a subspace is something is a vector space. So we're using the word, notice the space. You're using the word space. So using the word space is not easy. You have to have proper permissions in order to use the vector in the word space. So this means that the subspace is a vector space. A vector space in itself. It's a vector space in itself. And it's closed, so-called closed. So why am I using the word closed? It is closed under addition. It's what closed under addition, add, and scalar multiplication. So I would tell the camera to go a little backwards and show these all things properly. So that a vector space in itself is closed under addition and scalar multiplication. Closed means that if you do addition of vectors and scalar multiplication, it is closed under, and then the result also will lie in the subspace. The question comes, okay, fine, in definitions it sounds good, it's nice, but what about the examples? So let's talk about examples. So examples in, let's say now we'll start with R3 in the three-dimensional space. So in the R3, well, okay, so you need to have finding a subspace. Well, one thing you notice, the trivial subspace is the null space. Not the null space. Actually, that's a word that we will come through in the later parts of vector spaces. In later parts of vector spaces. So that's I'm not going to use that word. The space, the zero vector space, zero vector. So you can add two zero vectors, you will get a zero vector. You can multiply the zero vector by a scalar, you will get a zero vector. So that is the first subspace in I think Rn. In Rn, but now let's talk about and one more thing. And another trivial subspace that's obvious. Trivial, I think, I don't know what the word exactly means, but it means obvious. So another obvious subspace is the R3 itself. So you take the whole thing itself, or you take nothing of that. So that is the R3 itself. And the third is, this is important. It's a plane. Why a plane? Because let's say you have two vectors in the three-dimensional space. Okay, so this is x, y, z, and you have two vectors, and if you take the linear combinations, they're gonna form a plane, a nice plane. But there's one problem. If you take plane not passing through the origin, then they will not be a good vector. It will not be a subspace, to be honest, because if you multiply that by 0, you're gonna get 0, but that's not in the plane. If it's not passing through the origin, then it is not a subspace. So we have to emphasize here that the plane through the origin. Okay, so that was about R3. Now what about R4 and higher dimensions? So about R4 and higher dimensions. Actually, this lecture is a little bit faulty, to be honest, because I'm using the word dimensions over here without even telling you what the meaning is of dimensions in linear algebra. So it's not the usual meaning of the number of vectors you have, for example, the x, y, and z. So the number of axes is equal to the number of dimensions. That's what you're thinking, but that's not so. Okay, so even the subspace could be of matrices. It could be a space of matrices, not of numbers. So that is also a thing that should be noticed. Okay, so now what about higher dimensions? In higher dimensions, you will have something, what is called a hyperplane. A hyperplane. So hyperplane is nothing but giving words to our emotions, to our feelings. That the hyperplane is nothing but a plane like structure, a plane like thing in Rn. Okay, so that is to be thought of when I say the word hyperplane through the origin, obviously. So now we are convinced that subspaces could be of three types. One is the zero vector, is the these two are the trivial subspaces, the whole space itself, and next is the plane through the origin. A plane through the origin, or a hyperplane, as I said here, a hyperplane through the origin. So that was about the subspaces. So now let's move forward. Now, what else could be a subspace? So I would like to discuss more examples rather than speaking in the air. If you consider the system, if you have a matrix, a nice matrix A, you multiply it by the column vector x, and you get 0. So this is nothing but a system of linear equations written in the matrix form. So this is a column vector of variables. So then you see the column vector of variables. And now for what x? The question is for what x is ax equals to 0. So how do we see that question over there? Now what do we do with that question? Well, strictly speaking, there could be two options. The first option could be the trivial solution, and that would be that all of the x is 0. So that means all x is 0. So that means all x is 0. Okay, and the second is a non-trivial solution. So what do we mean by a non-trivial solution? So let's look at this problem at a totally different framework, totally different framework. So let's give this matrix, let's take a matrix, an arbitrary matrix over here. say it's A11, A12, A13, or let it be only 2, A21, A22, and this is a 2 by 2 matrix. So this should be let's say x1, x2, x3, and that is 0. So how can we write that? Matrix multiplication is in two ways. As the reader, the viewer already knows, I assume he already knows that matrix multiplication is two ways. One is the row picture, the column picture, and the matrices by the multiplication by dot products. So you see, if I use the multiplication by columns, then this thing over here is nothing but the linear combinations of the columns. Linear combination. It's a linear combination of the columns. So this linear combination. So if we are in the R2 space, in the R3 space, actually here we are in the R2 space. So if we take any two vectors, they are likely to span the whole space. And you see, if it would be R3, then also it would create a plane which is passing through the origin, since there's a trivial solution also. So you see, these axes create a subspace. So our conclusion is that the space of solutions is a subspace. So that was about vector spaces. That was about vector spaces. That was about vector spaces and subspaces. So what next? That means that's enough for this lecture, and I would like you to continue, and then I would like you to view and I would like you, any of you who want to learn linear algebra in a very systematic and a very nice approached way. I would like you to please view me, and I possibly making very big mistakes in the lecture. I'm nothing more than a student of linear algebra. I'm just a 12th grader. I'm just a 12th grader in India. So excuse me if I do any mistakes. Actually, I'm not a good lecturer, I know, but I like to share knowledge. Knowledge is made to share. Okay, so anyways, I would post another video continuing the knowledge, continuing this vector spaces. I would post another video. This was vector spaces part 1, and I would post another video called vector spaces part 2, and then we would continue with linear algebra for over time. So that's for the day. Good day, and thank you for watching me.